The fastest techniques are always discovered by accident, not because they are meant to be hidden, but because they appear in places no one thinks to look, in quiet laboratories where equations were never meant to explain meaning, in forgotten footnotes of physics papers written for no audience beyond a handful of specialists, in moments when scientists were not trying to change the world, but simply trying to understand why reality behaves the way it does when no one is watching. For most of human history, the universe was assumed to be passive, a vast mechanical stage where events unfolded according to fixed laws, indifferent to thought, intention, or awareness. You were born into it, you moved through it, and eventually you disappeared from it. Your inner life was private, sealed off from the external machinery of stars, atoms, and time. The universe did not care what you believed, it simply was. Then, in the early 20th century, something deeply unsettling happened. Physicists began to notice that at the smallest measurable scales, reality did not behave like a machine at all. It behaved more like a question. Particles refused to exist in a single state. Outcomes could not be predicted, only described in terms of probability. And most disturbing of all, the act of observation itself appeared to change what was being observed. At first, this was treated as a technical inconvenience, a flaw in measurement, a mathematical oddity. But as experiments became more precise, the pattern refused to disappear. Instead, it grew clearer. The universe, at its foundation, was not fully formed until something looked at it. This was not philosophy. This was not mysticism. This was experimental physics. Electrons behaved differently when measured. Photons altered their behavior when observed. Entire systems collapsed from clouds of possibility into single outcomes the moment information was extracted. The universe, it seemed, was not merely unfolding, it was responding. And buried inside this realization was a dangerous implication. If observation matters, then awareness matters. If awareness matters, then the boundary between mind and matter is not as clean as we once believed. And if that boundary is permeable even slightly, then reality is not something that simply happens to you. It is something you participate in. For decades, this idea remained confined to academic debate. Physicists argued over interpretations. Philosophers argued over meaning. The public heard fragments, often distorted into slogans that promised too much and explained too little. Most of it was dismissed as metaphor, a poetic way of describing math, nothing more. But quietly, methodically, the experiments continued, and over time a small number of researchers began to notice something else. Not just that observation changes outcomes, but that timing, expectation, and informational context appeared to influence how quickly systems resolved into stable states. Some quantum processes settled almost instantly. Others lingered in uncertainty, and the difference was not always explained by energy, temperature, or external force. In other words, reality seemed to have a speed limit for becoming real. And under certain conditions, that limit could be pushed. What you are about to hear is not a promise of miracles. It is not a claim that thoughts magically bend the universe at will. It is a careful reconstruction of how modern physics, neuroscience, and probability theory intersect in ways that suggest something far stranger than wishful thinking and far more constrained than fantasy. There is a fastest way for outcomes to crystallize, a narrow window where probability collapses with unusual efficiency, a technique not invented by mystics or motivational speakers, but inferred from how reality itself behaves under observation. And once you understand it, the unsettling part is not how powerful it sounds. The unsettling part is how ordinary it is, how often it may already be happening, and how little attention we have paid to the conditions that make it possible. This is not about manifesting anything you want. It is about understanding the precise circumstances under which the universe stops hesitating. Before we begin, take a moment to subscribe to the channel, like this video, and leave a comment below answering one simple question: which part of the country are you watching from? Chapter 1: When the Universe Refused to Make Up Its Mind. The story begins with a mistake, or at least something that looked like one. In the late 19th century, physics was considered nearly complete. The laws of motion had been written. Electromagnetism had been unified. Thermodynamics explained heat and energy with impressive precision. Many prominent scientists believed that all that remained was refining measurements to a few more decimal places. Then came a series of experiments that refused to cooperate. When researchers began studying light at very small scales, they encountered contradictions that made no sense within classical physics. Sometimes light behaved like a wave, spreading out and interfering with itself. Other times it behaved like a particle striking detectors as discrete packets of energy. This dual behavior was not just confusing. It was logically incompatible with the assumptions of the time. The problem worsened when scientists turned their attention to matter itself. Electrons, long thought to be tiny solid objects, exhibited the same dual nature. They could diffract like waves, yet appear as localized impacts when detected. The more carefully physicists tried to pin down what an electron was, the more it slipped through their conceptual fingers. The mathematical framework that emerged to describe this behavior was quantum mechanics. It worked extraordinarily well. It predicted experimental results with astonishing accuracy, but it did so at a cost. The equations described probabilities, not certainties. They offered wave functions, not trajectories. And they refused to tell a simple story about what was actually happening between measurements. One of the most troubling features of quantum mechanics was something that came to be known as the measurement problem. According to the theory, a quantum system exists in a superposition of all possible states until it is measured. Only then does it collapse into a single outcome. But the theory itself does not specify what counts as a measurement, or why collapse happens at all. Is it the interaction with a measuring device? Is it the extraction of information? Is it the involvement of a conscious observer? The equations are silent. This silence led to fierce debate. Some physicists argued that collapse is not a physical process at all, but merely an update of knowledge. Others proposed that all possible outcomes occur in branching universes. Still others suggested hidden variables that restored determinism behind the scenes. Each interpretation preserved the mathematics while offering a different story about reality. What none of them denied was the empirical fact that observation changes outcomes. One of the clearest demonstrations of this is the double-slit experiment. When particles such as electrons are fired through two narrow slits without being observed, they produce an interference pattern characteristic of waves. When detectors are placed to observe which slit each particle passes through, the interference pattern disappears, and the particles behave like classical objects. The act of measurement does not merely reveal which path the particle took. It changes the behavior of the system. Reality reorganizes itself in response to information being acquired. At first, this was treated as an all-or-nothing phenomenon. Either a system is measured or it is not. Either it collapses or it remains in superposition. But as experimental techniques improved, researchers began to explore intermediate cases, weak measurements, partial information, delayed choice experiments where the decision to measure is made after the particle has already passed through the apparatus. The results were deeply counterintuitive. In some cases, particles behaved as if they anticipated future measurements. In others, the degree of observation influenced the degree of collapse. The boundary between possibility and actuality became increasingly blurred. This is where time enters the story. In classical physics, time is a neutral backdrop. Events occur in sequence, but the passage of time does not affect the nature of physical laws. In quantum systems, however, timing can be everything. The duration of coherence, the rate of decoherence, and the speed at which information is exchanged with the environment all determine how quickly a system resolves into a definite state. Decoherence is often misunderstood as collapse itself. In reality, it is the process by which a quantum system becomes entangled with its surroundings, effectively losing its ability to exhibit interference. Decoherence happens extremely quickly for macroscopic objects, which is why we do not observe quantum superpositions in everyday life. But it is not the same as collapse. It explains why certain outcomes become stable, but not why one outcome is realized instead of another. What matters for our purposes is that decoherence has a rate, and that rate depends on how information flows. In controlled laboratory settings, physicists can slow decoherence down or speed it up by manipulating the environment. Isolating a system preserves superposition. Introducing noise accelerates collapse. Crucially, extracting information, even indirectly, plays a central role in this process. This suggests something subtle but profound. The universe does not rush to make decisions. It hesitates, it explores possibilities, and the speed at which it commits to an outcome depends on how much information is being demanded of it. In other words, reality has inertia. This inertia is not about mass or energy. It is about uncertainty. And uncertainty can persist longer or shorter depending on context. When people speak loosely about manifestation, they often imagine the universe as a vending machine responding to desire. That picture is scientifically indefensible. But there is another way to frame the idea that aligns more closely with what physics actually describes. Instead of asking whether thoughts cause events, we can ask how informational states influence probabilistic systems. Instead of imagining intention as a force, we can consider it as a constraint, a narrowing of possibility space, a way of reducing entropy in the selection of outcomes. From this perspective, the question is not whether the mind creates reality, but whether the mind participates in the same informational economy that governs physical systems. Neuroscience adds an important layer to this discussion. The human brain is not a passive receiver of sensory data. It is an active prediction engine. It constantly generates models of the world and updates them based on incoming information. Perception itself is a form of inference shaped as much by expectation as by stimulus. This predictive processing means that awareness is not just about observing what is there. It is about anticipating what will be there. And anticipation has measurable effects on behavior, attention, and decision-making. At the level of the organism, this is uncontroversial. Expectations influence reaction times. Beliefs shape actions. Mental states alter physiological responses. None of this requires invoking quantum mechanics. The question is whether similar principles apply, even weakly, at the boundary between observer and observed in physical systems. Most physicists would caution against drawing a direct line from human consciousness to quantum collapse. There is no evidence that the brain exploits quantum effects in a way that influences external systems at a distance. Claims to the contrary are speculative at best. However, there is evidence that information, broadly defined, plays a central role in physical law. Black hole thermodynamics, for example, treats information as a fundamental quantity. The holographic principle suggests that the information content of a region of space can be described on its boundary. Quantum information theory reframes entanglement, measurement, and computation as informational processes rather than mechanical ones. In this framework, the universe is not a machine made of stuff. It is a system that processes information. And in any information processing system, the speed of resolution depends on constraints, inputs, and feedback loops. This brings us to the core idea underlying the fastest quantum manifestation technique ever recorded. Though the phrase itself is a modern label applied to something much older, there are moments when probability collapses unusually fast, when systems move from uncertainty to certainty with minimal delay, when outcomes feel sudden, decisive, and irreversible. In physics, these moments are often associated with critical thresholds, phase transitions, or tipping points. Water does not gradually become ice molecule by molecule. It remains liquid until a specific condition is met, then reorganizes almost instantly. Magnetic materials do not slowly align their domains. They snap into order once a critical temperature is crossed. Lasers do not emit coherent light until population inversion reaches a precise level, at which point amplification becomes explosive. These are not violations of physical law. They are expressions of it. What they reveal is that speed is not always about effort or force. Sometimes it is about alignment, about bringing a system into a state where the next step is inevitable. In quantum systems, this inevitability is expressed as a rapid collapse of the wave function, not because something pushes it, but because uncertainty can no longer be sustained. The fastest manifestation in this sense is not about wanting harder. It is about removing ambiguity. It is about creating conditions in which only one outcome remains viable. This is not something individuals can do to the universe at large, but it is something systems do all the time, including biological and cognitive systems. Human decisions, for example, often appear sudden. A person deliberates for days, weeks, or years, then acts in a single moment. From the outside, it looks like a leap. From the inside, it feels inevitable. The brain has been accumulating evidence, weighting probabilities, and narrowing options until one path dominates. The moment of decision is not the beginning of the process. It is the end of it. When people describe experiences of rapid change in their lives, they often focus on the moment everything shifted, a phone call, a realization, an opportunity. But the groundwork was laid long before. The system was primed. In physics, priming a system means preparing it in a particular initial state. In quantum experiments, this is done with extraordinary care. Lasers are stabilized. Temperatures are controlled. Noise is minimized. Only then can precise outcomes be observed. The fastest results come from the most carefully prepared conditions. What modern discussions of manifestation often miss is this preparation phase. They focus on intention as if it were the trigger, when in fact it is the final constraint that allows a system to resolve. In scientific terms, the key variable is not desire but coherence. Coherence refers to the degree to which components of a system maintain a fixed-phase relationship. In quantum systems, coherence allows superpositions to persist. In biological systems, coherence appears in synchronized neural activity. In social systems, coherence emerges when individuals align their actions toward a common goal. Coherence reduces noise, it amplifies signal. It allows small influences to have outsized effects. When coherence is high, systems change quickly. This is as true for a laser cavity as it is for a human mind. The fastest quantum manifestation technique, stripped of mystique, is the process of maximizing coherence while minimizing contradiction. It is about reducing internal interference so that when an outcome becomes available, the system transitions without delay. This does not mean the universe bends to personal will. It means that when probabilities shift in your favor, you are positioned to move with them instantly. Physics does not grant wishes, but it does reward alignment. In the chapters that follow, we will examine how this principle appears across disciplines. In quantum experiments, in neuroscience, in complex systems, and in historical moments when change accelerated beyond expectation, we will separate metaphor from mechanism. We will identify where popular narratives overreach and where they underestimate how strange reality already is. And we will return again and again to the same unsettling insight. The universe is not slow by default. It is cautious. And when caution is no longer necessary, things happen very fast indeed. Chapter 2, here the speed of collapse, to understand why some outcomes arrive with startling speed while others seem to stall indefinitely. Physics forces us to confront an uncomfortable idea. Reality is not continuously becoming real. It does so in bursts. Long stretches of ambiguity are punctuated by moments of sudden resolution. The universe hesitates, then commits. In classical intuition, change is smooth. Causes lead to effects through continuous chains. If something happens quickly, we assume a large force was applied. If something happens slowly, we assume resistance. Quantum physics dismantles this intuition. At the fundamental level, speed is not always about force. It is about probability density and the conditions under which probability can no longer remain spread out. In quantum mechanics, the evolution of a system is governed by the Schrödinger equation. This equation is deterministic. Given an initial wave function, it predicts how that wave function evolves over time with perfect precision. But the equation does not describe what we actually observe. What we observe are outcomes, definite positions, energies, spins. To get from the evolving wave function to an observed result, something else must happen. The wave function must collapse, or at least appear to. This apparent collapse is not described by the Schrödinger equation. It is introduced as an additional rule. When a measurement occurs, the wave function discontinuously reduces to a single eigenstate corresponding to the observed value. The probabilities encoded in the wave function suddenly become irrelevant. One outcome is realized. All others vanish. What is striking is how quickly this happens. Collapse is effectively instantaneous. There is no gradual transition from uncertainty to certainty. One moment the system allows multiple futures, the next only one remains. This abruptness has troubled physicists for more than a century. It seems to violate the smooth continuity that governs every other physical process. But repeated experiments confirm it. Once sufficient information is extracted from a system, ambiguity does not linger. The speed of collapse raises a deeper question. Why does the universe tolerate uncertainty at all, and why does it abandon it so decisively? One way to approach this question is through the lens of information theory. In this framework, physical systems are not just arrangements of particles and fields. They are carriers of information. States encode possibilities. Measurements extract bits. Collapse corresponds to an update in the information available about the system. From this perspective, uncertainty is not a flaw. It is a resource. A system in superposition contains more potential information than a system in a definite state. Maintaining that superposition requires isolation. The moment information leaks into the environment, uncertainty begins to decay. This leakage does not have to involve a conscious observer. Any interaction that correlates the system with something else counts. A photon scattering off an electron, a molecule vibrating in response to heat, a detector registering a signal. All of these interactions spread information outward. The rate at which information spreads determines how long uncertainty can survive. In laboratory settings, physicists have learned to manipulate this rate. By cooling systems to near absolute zero, they reduce thermal noise. By shielding experiments from electromagnetic interference, they limit unwanted interactions. By using error-correcting codes in quantum computers, they actively suppress decoherence. These techniques do not eliminate collapse, but they delay it. They stretch the time during which multiple possibilities coexist. The inverse is also true. When information extraction is aggressive, collapse accelerates. Strong measurements force systems into definite states almost immediately. Weak measurements allow partial information to be gathered without fully collapsing the wave function. But even then, repeated weak measurements add up. This reveals a crucial principle. Collapse speed is not fixed, it depends on context. In some situations, the universe is remarkably patient. In others, it resolves ambiguity with ruthless efficiency. This variability invites a broader interpretation. Perhaps collapse is not a mysterious intervention, but the natural consequence of informational pressure. When the environment demands clarity, the system provides it. This idea becomes even more compelling when extended beyond isolated particles to complex systems. Consider phase transitions. At a critical point, a system undergoes a rapid reorganization. The underlying components were always capable of the new arrangement, but competing configurations prevented it from dominating. As conditions change, one configuration becomes overwhelmingly favorable. The system snaps into place. The speed of this transition can be astonishing. Magnetic domains align. Superconductivity emerges. Chemical reactions ignite. These are not gradual drifts. They are sudden reorganizations driven by probability landscapes reshaping themselves. What matters is not how long the system existed before the transition, but how sharply the probabilities shifted. In this sense, the fastest changes occur when uncertainty collapses under its own weight. This principle applies not only to physical matter, but to information processing systems of all kinds. Neural networks, whether biological or artificial, often exhibit sudden learning. A model struggles, makes errors, appears stuck. Then, with one more data point or adjustment, performance improves dramatically. The underlying parameters did not change much. What changed was the coherence of the internal representation. Human insight follows a similar pattern. A person wrestles with a problem, gathers information, considers alternatives. Then clarity arrives seemingly all at once. The solution feels obvious, even inevitable, in hindsight. The moment of understanding is a collapse of cognitive uncertainty. In all these cases, speed is an emergent property. It arises when competing possibilities are pruned until only one remains viable. This brings us closer to what is often described imprecisely as manifestation. In popular discourse, manifestation is framed as a way of causing external events through intention alone. This framing invites skepticism, and rightly so. There is no credible evidence that mental states directly manipulate distant physical systems in violation of known laws. But if we reinterpret manifestation as the rapid alignment of a system toward a particular outcome, the concept becomes more grounded. Consider a person navigating a complex environment. Opportunities exist, but they are probabilistic. Many paths could unfold. The speed with which a favorable outcome occurs depends not only on external circumstances, but on how the person perceives, interprets, and responds to those circumstances. Attention plays a critical role here. Attention is a limited resource. Where it is directed determines which information is processed and which is ignored. By focusing attention, the brain effectively increases the signal-to-noise ratio for certain patterns. This does not change the external world directly, but it changes how quickly relevant information is detected. Expectation further shapes perception. Experiments in psychology show that people are more likely to notice stimuli that align with their expectations. This is not because the stimuli were not present before, but because they were filtered out. From an informational standpoint, attention and expectation act as constraints. They narrow the space of possibilities that are considered relevant. This narrowing accelerates decision-making and action. When many individuals align their attention and expectations, collective effects emerge. Markets move rapidly. Social trends spread, technological adoption accelerates. These phenomena can appear sudden and dramatic, but they are the result of probabilistic alignment across many agents. No single person controls the outcome, but coherence amplifies speed. Returning to quantum systems, coherence is the property that allows superpositions to exist. When coherence is lost, the system behaves classically. When coherence is preserved, quantum effects dominate. In both cases, coherence is about consistency, about phases lining up, about competing possibilities not interfering destructively. The fastest quantum processes are those with high coherence and strong constraints. For example, stimulated emission in a laser occurs when an incoming photon induces an excited atom to emit a photon with the same phase, direction, and frequency. This process is incredibly fast and efficient because the system is already primed. The atoms are in a specific excited state. The cavity enforces boundary conditions. The incoming photon does not create order from chaos, it reinforces existing order. The result is amplification at the speed of light. This is a powerful metaphor, but it is also a precise physical mechanism. The implication is not that intention creates outcomes, but that prepared systems respond rapidly to aligned inputs. In everyday language, preparation is often overlooked. People focus on triggers, not on states. They ask what caused an event, not what made the system susceptible to that cause. The fastest changes occur when susceptibility is maximized. In quantum experiments, this means preparing initial states with care. In cognitive systems, it means cultivating clarity, reducing internal conflict, and aligning beliefs with actions. In social systems, it means shared narratives and synchronized behavior. None of this requires invoking supernatural forces. It is a consequence of how complex systems process information. The danger arises when these ideas are oversimplified. When people are told that belief alone is sufficient, they may ignore the structural constraints that shape outcomes. They may mistake correlation for causation. They may attribute random success to personal power. Science demands a stricter standard. The question is not whether rapid outcomes can occur. They clearly can. The question is under what conditions they occur reliably. Physics suggests that rapid resolution happens when uncertainty is no longer sustainable, when competing possibilities have been sufficiently suppressed, when the cost of ambiguity exceeds the cost of commitment. In quantum terms, collapse happens when a system becomes entangled with too many degrees of freedom to maintain coherence. In practical terms, decisions happen when evidence accumulates beyond a threshold. Actions happen when hesitation becomes more costly than risk. The fastest manifestation, then, is not an act of creation, but an act of elimination. It is the removal of alternatives. This is why sudden breakthroughs often follow long periods of apparent stagnation. The system was not idle. It was exploring. It was accumulating constraints. It was reducing entropy. When the final constraint arrives, the transition is immediate. Understanding this reframes how we think about speed. Speed is not about rushing. It is about readiness. The universe does not reward impatience, it rewards coherence. In the next chapter, we will examine how time itself behaves differently in systems near critical thresholds, and why subjective experiences of sudden change often coincide with objective shifts in probability landscapes. We will explore how modern physics understands time not as a uniform flow, but as a variable shaped by interaction, information, and perspective. And we will see why moments that feel instantaneous are often the culmination of processes that began long before anyone noticed.